Up to this point in the course, we have been starting from a fundamental principle with the choice of system that has typically been a single object. Moreover, we have typically been thinking of that object as a single particle, where we focused on the translational motion. Today we're going to start broadening this notion of system by considering cases where we have multiple particles. We'll see that in these cases there's an energy that contributes to the total energy of multi-particle systems. That new energy is called the potential energy. To start, let's consider the situation where a ball of mass m falls near the surface of the Earth. Let's say that the mass is 1 kilogram, and let's say the ball starts at rest and drops a distance of 2 meters. We'll neglect air resistance here. Let's apply the energy principle here to find the kinetic energy of the ball when it is in its final state, 2 meters below the starting point. If we make our standard choice of system as just the ball, then we know the Earth is the only agent in the surroundings that interacts with the system. So to use the energy principle to find the final kinetic energy of the ball, we need to compute the work on the system by the weight force. See if you can compute this work. Since the weight is a constant force, the work is just the scalar product of the weight and the displacement. So we find the work here, meaning the weight force transfers this amount of energy to the system. Now in this case, when we apply the energy principle, we know the change in system energy delta E is just equal to the change in kinetic energy. And since the ball starts at rest, we can solve for the final kinetic energy of the ball, which answers the question we posed. Now let's take this same situation, but choose the system differently. Let's choose the system to include both the ball and the Earth. Again, we can ask the question, what's the final kinetic energy of the ball? Again, starting from our energy principle, we need to identify the agents in the surroundings and compute the work done by the surroundings on our system. Let's compute the work done by the surroundings on this multi-particle system. The answer here is 0. There's nothing in the surroundings interacting with our system, so no agents, no interactions, no energy transfer by forces, so the total work W is 0. Okay. Then what can we say about the change in kinetic energy of our system? Give this question a try. The energy principle tells us directly that since the work done is 0, the change in the total energy E is also 0. Now, if we made the assumption that delta E is equal to the total change in kinetic energy, then we might conclude that the change in kinetic energy of the system is 0. But that would be wrong, because as we already found, the ball clearly has a positive change in kinetic energy. Using a different choice of system isn't going to change that. As we'll discuss in a moment, the interaction of the ball with the Earth is too weak to change the kinetic energy of the Earth. So the total change in kinetic energy of the system of the ball plus the Earth, should have the same total change in kinetic energy as the ball, which, as we know, is a positive change in kinetic energy. How can that happen if the work done is 0? Is the energy principle wrong here? Nope. Delta E equals W is completely correct. The change in the system energy is 0 since there is no energy transfer between the multi-particle system and the surroundings. The difficulty here is that the change in delta E involves more than just changes in kinetic energy. There's another energy we need to account for here in our multi-particle system. Let's see how we can arrive at this other energy. Consider this more general example where we have 3 particles, each of which can interact with each other. We'll assume here that those interactions are reciprocal and follow Newton's third law, so that the interactions expressed as forces on different particles can be related. For example, the force on particle 1 due to particle 3 has the same magnitude and is oppositely pointed to the force on particle 3 due to particle 1. The same holds for the interactions between particles 1 and 2 and particles 2 and 3. In addition, let's assume each particle has an interaction with one or more agents that we don't see identified here. In this case, for example, a force F1 exerted by some agent on particle 1, a force F2 exerted by some agent on particle 2, and a force F3 exerted by some agent on particle 3. Moreover, let's say this is the initial state and this is the final state. Let's apply the energy principle in the way we know how to well. Choose our system to consist of a single particle. Let's start with particle 1. With only one particle, the change in system energy, delta E1, is just equal to delta K1, the kinetic energy change of particle 1. And by the energy principle, that would be equal to the total work done by all agents acting on particle 1. In this case, there are 3 agents exerting forces that could be doing work. And so here's what the energy principle would look like for particle 1. We can do the same thing for particle 2, meaning start all over with the energy principle with particle 2 as our system, and flesh out the energy principle using the same arguments, but focused on system 2. This would be the result. And we can repeat this yet again for particle 3 as our single particle system. And here is the result for that. Now, to write down the multiparticle system case where our system contains all 3 particles, we would simply add up all 3 of these equations together. We can do this by just adding all the left-hand sides of these equations together. We need to do the same thing for the right-hand sides of the equations, and we would get this. There are a lot of terms here, but notice we can collect these into 2 groups. This group is the work done by agents in the surroundings, meaning this work represents the transfer of energy between the multiparticle system and something else in the surroundings. This is our usual definition of work. However, the other group of terms represent work done by one part of the system on another part of the same system. Collectively, this represents energy changes inside our multiparticle system. And so, to make this clear, we will treat these terms differently. Now, for certain interactions like gravitational or electric interactions, these terms represent energy changes we'll call changes in potential energy, which will symbolize as delta U. Each potential energy change for a given interaction inside the system is equal to minus the work associated with that interaction. Rewriting our multiparticle energy principle using changes in potential energy and rearranging terms with a little algebra, we see that our multiparticle energy principle tells us that the change in the total energy E of our multiparticle system is equal to the sum of the kinetic energy changes plus the sum of the potential energy changes. This must, as always, be equal to the energy transfers to and from the surroundings, which here is the total work done by the surroundings on the multiparticle system. All this may seem a bit abstract, so we'll illustrate with lots of examples in future lectures. For now, let's revisit our example of the falling ball, with the choice of system of the ball plus the earth. Here, as we said, the surroundings are doing no work as there are no agents in the surroundings exerting forces. So, as we found earlier, this means the change in the total system energy, delta E, must also be 0. Now, however, we know that delta E consists of both the changes in kinetic energy of the particles in the system plus the change in potential energy associated with the gravitational interaction between the ball and the earth, now within the system. Let's handle each of these terms in turn. First, let's note the total change in kinetic energy for the system is the sum of the kinetic energy changes for the ball and the earth. Now, in this case, we can neglect any kinetic energy change of the earth. The only way the Earth's kinetic energy can change is by gravitational interaction with the ball. We know from reciprocity both the ball and the Earth experience the same magnitude of gravitational force, but because the Earth is so much more massive, the gravitational force of the ball on the Earth will hardly affect the Earth's motion. So, in effect, delta K Earth is 0. When working with multiparticle systems, there are times we can rule out terms in the energy principle by using arguments like these. However, it's good practice to always start with all the terms present. In this case, start with all the kinetic energy changes, and then, if possible, state explicitly the physical reasons, at least to ourselves, why we can make such simplifications. Now let's look at the change in potential energy. There's only one delta U here because there is only one interaction, the gravitational interaction between the ball and the Earth, and that is, by definition, related to all work associated with the interaction. The work done on the ball by the Earth and the work done on the Earth by the ball. Also, both work terms involve the weight force, and we can use reciprocity here. So you might think the two terms would cancel, but they don't because the displacements of the ball and the Earth are not generally the same. Again, because the Earth is hardly affected by the ball's gravitational pull, the work done by the ball on the Earth will be negligible. So we end up with this expression for the change in potential energy. As a side note, it's common to choose a coordinate system with up in the plus y direction. So the change in gravitational potential energy here, delta Ug, for the case with the ball near the surface of the Earth can be written as mg delta y. And so our multiparticle energy principle boils down to delta K ball plus delta U gravity equals 0. The change in gravitational potential energy is negative here. So the change in kinetic energy must be positive, such that the total change in energy of the system, delta E, is 0. This all makes physical sense. We can now use this expression to solve for the final kinetic energy of the ball, and we find we get the same result as before when we just chose the ball as our system. Now for this example, the choice of a multiparticle system didn't really teach us anything new. However, we will encounter cases where making the choice of system to include multiple particles will help us learn new physics that would be difficult to access if we only restricted our choice of system to include single particles. We'll illustrate this in examples in lectures coming up soon.